Alright, so let's continue with 4.3, the exercises. These are done in the same order. You'll see them on your WebAssign assignment. So they ask you, where is it increasing? It's increasing from 1 to 3 and 4 to 6. And where is it decreasing? From 0 to 1 and 3 to 4. It's concave up till this point here, and then concave down to here, and then concave down there. You have one point in which concavity is changing, and so you have an inflection point at the point 2, 3. Suppose you're given a formula for f. How do you determine if it's increasing or decreasing? Use the increasing or decreasing first derivative test. How do you determine whether the graph is concave up or down? Well, you use the concavity second derivative test. How do you locate inflection points? Well, that's anywhere where the concavity changes, and to find them you have to plug that x value into the original function to get the y coordinate. Now this one's a little tricky. This one says the derivative of f prime is shown here. This is not f, but f prime. What interval is the original function increasing? Well, it's increasing where the first derivative is positive. So it's increasing from 0 to 1 and 3 to 5, and decreasing where it's negative. Alright? Now, what are the values of x? Does the function have a local max or a local min? Well, since f prime of x equals 0 at x equals 1 and 5, and f prime changes from positive to negative, f changes from increasing and decreasing and has a local max at 1 and also at 5. Now since f prime equals 0 at x equals 3, and f prime changes from negative to positive, then f changes from decreasing to increasing and has a local min at x equals 3. Number 7, they say the curve of this is f. How do you find the inflection points? Well, it's where concavity changes. Concavity is down until here, so there's an inflection point there. Concave up, and then it changes to concave down here, so there's an inflection point at 3 and 5. Alright. Now, if the curve of this is the first derivative, how do you find the inflection points? Well, it's where the first derivative goes from increasing to decreasing or decreasing to increasing. Now, how do you find the inflection points for if the curve is the graph of f prime? Well, it's where it crosses the x-axis is where you find your inflection point. Alright, so now they're just asking you to find increasing, decreasing, and max or min. So you take the first derivative, factor, set it equal to 0, find your critical numbers, divide up your number line, and you check a value in each region with the original or the factored form. And wherever it's positive is where it's increasing. Wherever it's negative, it's decreasing. And you have a local max at 1, 6 actually, and you have a local min at 4, or 4, negative 21. Same thing here. Take the first derivative, set equals 0, divide up your number line. You can tell where it doesn't have a local max or min here, but it does have a local min there. Alright, you take the first derivative, factor it, divide up your number line, and do all your testing, and you can see where it's decreasing and increasing the local max and local min. Alright, you take the first derivative and solve for x, and you see where cosine equals sine, and that's at pi over 2, or pi over 4, and 5 pi over 4. So now you divide up your number line, and it's only divided up from 0 to 2 pi. And when you check something in this region, something in this region, something in that region, you get these signs, so now you can tell what's happening with max mins and increasing, decreasing. Same thing here, but they want you to use, now they're asking you to check for concavity. So you take the first derivative and then the second, and you set the second equal to 0, divide up your number line, concave down here, concave up there, and that's an inflection point since it changes concavity. 19, you take the first derivative and then you take the derivative again, and you get this guy, and where does it equal 0? At pi over 4 and 3 pi over 4, and you check each region in the most factored form, and you can see where it's concave up and down, and you've got 2 inflection points there. 21, remember the domain for natural log has to be positive, so you're looking for x values that give you positive for x squared plus 5, but x squared plus 5 is always positive, so your domain for this guy is everything. You take the first derivative and you get this. You take the second derivative and you simplify it and you get that in its factored form. And you get plus or minus square root of 5. On the bottom you don't get anything, but on the top you'll get plus or minus the square root of 5. Divide up your number line, check the regions, and now you know where it's concave up and down, and you know where you have inflection points. 23, you take the, now they're asking you to do everything. You take the first derivative and you find increasing, decreasing local max and mins. You take the second derivative, you find out where it's concave up and down, and inflection points. Same thing with 25. Note that x equals minus 1/2 is not in your interval, is not in your domain here, so you don't have to consider it. You only consider things greater than 1. When you take second derivative and set it equals 0, you only get 0 as a critical number, which isn't really a critical number because it's not in the domain of the original function. So this entire function is concave up always. It's always positive. This one, they take the first derivative, and it gets, this part gives you a minus 1/2, which helps you divide up the number line. And then here, this one ends up giving you only one critical number at -1. And you can see what your concave up and concave down are. 29 is they find the local max and mins using both the first derivative test. So you take the first derivative, divide it up, and you can tell where your local max or mins are. Now they want you to use those critical numbers of 0 and 1 into the second derivative. When you plug it in the second derivative and you get a positive, that means there's a minimum at that point. If you plug it in and you get a negative, that means it has a maximum at that point. Remember, if you plug a critical number into the second derivative and it gives you 0, it doesn't tell you anything. Alright, so 31, well, let's look at 35. 35, now they're asking you to graph it based on the information they give you. So if f prime is always positive, that means it's forever increasing. And f double prime is always negative, that means it's always concave down. So it's got to be curved that way, and it's got to be going up always. And this one's always decreasing, and it's always concave up, so it's got to curve that way. And now they're just adding more information here. When you have horizontal tangents, that means you have a max or a min at 0, well, possibly a max or a min, but you have a leveling off at 0, 2, and 4. And they tell us that it's increasing on this interval, decreasing on that interval, and so you know when it's going up and when it's going down. And then you also have to worry about concavity. Where is it concave up and concave down? So it's concave down to here, concave up to there, and concave down to there. Horizontal tangent at 5, it's decreasing and increasing, and then it's concave down, and then concave up, and then concave down. And it also has a horizontal asymptote. And this one, it's forever increasing, and it's concave up and then concave down. 43, they give you the graph there, and that's the graph of f prime. So now on what interval is f increasing? Well, it's where f prime is positive, so 0 to 2, 4 to 6, and greater than 8. And where it's negative is where it's decreasing. And now if you know that where it's increasing and decreasing, you can figure out where it has local max and mins. And you can also look at that and figure out that it has concavity from 0 to 3, and then from 3 to 6 it flips concavity, and 6 to 8, 6 or greater, it's even higher concavity. Alright, so 45, you take the first derivative, find your max or mins, your concavity, and inflection points, and it's all right there. Okay, 47, same idea. Okay, here's the initial question. Okay, and then we look at it a little farther, and then we finally get our answer as our graph here. 49, same idea. Take the first derivative, analyze it, take the second derivative, figure it out, and you get concave up and down, and you also get your inflection points. Same thing with 51. Okay, and then 53. Here's your original function. Notice it's minus infinity to 6 because what's underneath here has to be greater than or equal to 0. So you've got all these calculations and the second derivative, and it's always concave down. 55, same idea here. Local max and mins, concavity, inflection points. 57, first derivative, set it equal to 0, divide up your number line. You get your increasing and decreasing second derivative, simplify it as much as you can, factor it, and you get your inflection points as well as concavity. 59, take the first derivative, and notice here they want to check for asymptotes, and if you check for asymptotes at plus or minus infinity, you get y equals 1. If you check at 0, which is the place where this function is undefined, you find that you have vertical asymptotes at x equals 0. And then everything else is the same, first derivative, second derivative, and now you're able to state everything that you found based on the original function. Same idea here. You want to do the vertical asymptote, and you get a horizontal asymptote at y equals 1, you get a vertical asymptote at x equals 0. When you take the first derivative and set it equals 0, and you get that places where it's increasing and decreasing, f double prime as well. And here's what your answers are. Where it's increasing, there's no decreasing. No local max or mins, it has concave up, inflection points, and there's your graph. And it has a vertical asymptote because the limit as you approach 0 goes to infinity. 63. Again, they want you to check for asymptotes. You find a horizontal asymptote at y equals 0. There's no vertical asymptote. First and second derivative test, and you get your answers here. 65. Okay, so if you analyze this, you see that your domain is from 0 to e only. It doesn't have a horizontal, but if you approach 0 from the right, it goes up to infinity, and I explain why. As if you approach e from the left, the other endpoint, you see that it goes off to minus infinity. So it has asymptotes at 0 and e. So you take the first derivative and you find it's always decreasing. You take the second derivative and you find that it's concave up and down in two different spots. And now here's all your information that you got from your answer there. And then 75, well, 77 is these questions are interesting. It says the president announced that the national deficit is increasing, but at a decreasing rate. So if something is increasing, it's always going up. But if its rate of increase is decreasing, that means it's slowing down about how fast it's going up, and so thus it has its concavity is down. That's what that basically is saying. Now it says test your K of t is a measure of knowledge you gain by studying for a test for t hours. Which do you think is larger? Difference between hours 7 and 8 or 2 and 3? Well, if you start out at the beginning studying and you don't know anything, you're going to gain knowledge quickly as you go along because you're learning a lot of information. But after a certain amount of time, you're going to know just about everything there is. And so if you're looking at the last hour in which you're doing the learning, it's not much of an increase at all, versus hours 2 to 3 is a lot faster of an increase. And most likely this is concave down, because your knowledge isn't going to keep increasing at an increasing rate. It's going to increase, but it's going to have a decreasing rate, which means it's concave down.